start with the same movie, which makes the point most graphically. So here's a numerical simulation of stirring of a viscous fluid. And we're okay. And the difference, the difference between the two protocols is this is clockwise, then counterclockwise, and these are both clockwise. So it's very clear that there's a fundamental topological difference between the two, and the behavior in terms of the fluid mixing and other dynamics are quite different. So we did an actual experiment with this. This is glycerin and dye. You can see the numerics are accurately mirroring the actual fluid motion. One way to think about these is in terms of braids. You do the space-time trajectory of the motion of the stirrers, and you see you can't deform this one into this one. So basically, these are different isotopy classes, as we'll discuss. And what I say to engineers, this is basically energetically the same, but one mixes much better than the other. And the question for this particular series of lectures is how much information can be deduced from the homotopy or isotopy class of the map, or in terms of the action on H1 or pi1. So sometimes a lot. So it turns out that you can prove that for this particular fluid motion, you can give a lower bound on the entropy. You can say what kind of periodic orbits have to be there, how they're linking around the stirrers, how the lengths of curves are growing exponentially, and variant measures. So you can say an awful lot, but you can't say virtually anything about this except there's a fixed point. So very much depends on the isotopy class. And as I said, sometimes you can say a lot, sometimes very little, and it depends very much on the action on the algebraic topology. So this is what I'm going to talk about, and I kind of talked about this last week. I'm going to talk today a little more about coordinates for the persistent dynamics, and also computing this data on the persistent dynamics. So going back to the original picture, we'd like to know, not just that this is different than this, but what the dynamics are here and how we describe those dynamics in a concise and clear way. So I need to stop the share and go to the other one. Okay, now how do I tell it to share? Here? Okay. Sorry. All right, so as I said, last week, primarily I talked about the fundamental group. And this time I'm going to talk mainly about homology. But as I said, I'm going to review the pi1 theory using a particular low dimensional example where you can kind of compute everything by hand. But most of the machinery was developed for surfaces or higher dimensional situations. All right, so here's a map. So it's a homeomorphism of the wedge of two circles. It's a homomorphism first on pi1. So pi1 is the free group on two symbols. So here's the action on generators. And we realize this as a map of the wedge of two circles in the simplest possible way. So because these has 4 letters here, the derivative is 4 everywhere. And we can all compute what the dynamics are. We divide each circle into 4 subintervals. Each interval wraps all the way around one of the circles. And so I model this with not a vertex shift. A vertex shift would have 8 symbols, but here we use an arrow shift. So we have all the transitions. A goes to itself in 3 different ways. It goes to B one way. B goes to itself like this, corresponding to the words we're specifying here. And as we always do in dynamics, we have infinite paths saying what Markov box you're in. And I'm going to use this matrix. This matrix is a more compact way than the 8x8 matrix to encode this shift. Okay, so how many fixed points do we have of the nth iterate? So we all know how to do this. We take the trace of the transition matrix to the nth and subtract 1. And then the question is, how much of this data is persist under homotopy? And remember, homotopy in this case can be computed by the action on pi1. So we all remember the Lefschetz formula. The Lefschetz formula, we need to know the action on 0th homology, which is just the identity. The action on 1st homology is just the abelianization. So it's exactly the transition matrix. The Lefschetz number is the action on H0 minus the action on H1. And so the Lefschetz formula tells us that we sum the indices of the fixed points and we get this Lefschetz number. The index is easy in the case because everything's a one-dimensional recolor. And so we see, in fact, that the Lefschetz formula, at least in absolute value, gives the number of fixed points. All right, so this is the good situation. Homology and the Lefschetz formula sees everything. All right, so, but if we look at the powers, there's a realization that everyone comes to about the Lefschetz formula, is that this is the Lefschetz formula of any G that's homotopic to phi1. It's the sum of the indices. But the problem with Lefschetz is it tells you the total index of all the fixed points, but it doesn't tell you how many there are. They all could be pushed into one fixed point. The kind of simple example is on the sphere. The class of the identity has Lefschetz number 2. You could have two index 1 fixed points. You could have one index 2 fixed points. So Lefschetz is very valuable. It's homology, so it's computable, but it can lose a lot of information in terms of distinct periodic points. All right, so here's another example just to, these are just examples to show you the action on homology. So here's a map on pi1 given by this. Once again, we put it on the wedge of two circles, and now A goes to A 2 times. This one's reversed, but we don't keep track of that. B times, so we get a 2, 2, 2, 2 as our transition diagram. This is our arrow shift picture, the transition diagram using the arrow shifts. So the paths here, it's the paths in here that matter. But this particular map is 0 on homology. All right, so Lefschetz very much fails. It gives us just one fixed point, one index 1. But when we pull out our Nielsen theory machine, we'll see that the number of fixed points actually is bigger than phi2. So when we perturb, it'll turn out that all the fixed points are preserved. In fact, all the periodic points are preserved. So the action on H1 gives us nothing. The action on pi1, in fact, gives us everything. So here's another example. It's almost the same, but now you hit A 3 times. And the transition matrix is this, right? Because A hits itself 3 times, hits B twice, etc. So the number of fixed points is our favorite formula to trace. The -1 is because of the overlap at the vertex. But this guy, the way I cooked it up, acts as the identity on homology. And so Lefschetz is dead 0 for all iterates. And as I said, nonetheless, when we have Nielsen theory, we will have all the periodic points persisting. All right, so here's Nielsen theory. I did this before, but as I said, I'm going to abelianize it. So I want to talk about it. So the idea is to subdivide the fixed point set into equivalence classes. And the equivalence classes, at least heuristically, can all be collapsed to each other. So here's the definition. We have a pair of fixed points. They're Nielsen equivalent if there's an arc from one to the other. And when you hit the arc with the map, these are fixed points, you hit it with the map, then the image arc is homotopic to the original one. All right, so obviously an equivalence relation. So that's what it means to be Nielsen equivalent. there's this arc that connects you, and under the map, it's homotopic to itself. As an equivalent definition, which is often very useful in the universal cover. So your Nielsen equivalent, if in the universal cover, you can lift the map and you can lift the fixed points. So the lift of the map fixes both fixed points. So the equivalence of these two is fairly easy to compute, to prove. So here's some consequences of the definition. So these are not hard, but first the Nielsen classes are relatively open in the fixed point set. So the Nielsen classes are separated by open sets. The Nielsen classes themselves are compact. And this implies that any given map has finitely many non-empty Nielsen classes. And again, I always have compactness here. Okay, so if you have something which is surrounded by an open set and it's compact and it's a fixed point set, you can define its index. All right, so a class is called essential if the index is not zero. And the main theorem is essential Nielsen classes persist under homotopy. Okay, so here's an example. Go back to our map phi1, and we want to understand its Nielsen classes. So how do we understand its Nielsen classes? Well, we need to understand its universal cover. So the universal cover of the wedge of two circles is this infinite valence 4 graph. And we want to look at the lift of our map. Well, this valence 4 graph is identified with the Cayley graph. We label the vertices by words. And when we act by the homomorphism, we send a letter to its image, a word to its word. That's how it acts on the cover. But that's exactly the same as our map phi0 when we lift it. We lift it and it works exactly like the action of the group homomorphism on the Cayley graph. All right, so what's the implication of all this? Now we know what the lift is. We know what the universal cover is. The important fact is that for this particular map, and for a lot of maps we're going to study, is that there's no cancellation in the action on pi1. So that means when you hit a word with the map, its length goes up by 4. All right, so I just did a computation, you just check it. So what this means dynamically and geometrically, that in the cover, lengths are stretched by 4. So when you have a pair of points in the cover and you hit them by the lift of the map, they get 4 times as far apart. All right, so that makes it very hard, makes it impossible for a lift to have 2 fixed points. So that's the implication here, that all the fixed points of phi to the n are in different Nielsen classes. All right, so again, easy proof. You do an induction, the nth iterate multiplies distances by 4 to the n, but they're fixed points, so their distance must have been 0, so they started the same. All right, so in the covering space, for all iterates, you can have at most 1 fixed point. So that means that all your fixed points are in different Nielsen classes of all iterates. All right, so this is going to be the strategy in a lot of the examples I'm going to give you is hyperbolicity in the universal cover has implications for Nielsen classes. All right, the other 2 examples I included in the talk because even though they act trivially on H1, they also have no cancellation and they also have growth in the cover. All right, so it's what I state here is also true for my other 2 maps. Irrespective of the fact that they act trivially on homology. All right, so this is what I claimed before. If you know these particular maps, Lefschetz doesn't give you much information, but Nielsen gives you a lot of information. All right, so we need 1 more ingredient, 2 more ingredients, is we need to worry about our periodic points as we perform a homotopy. There are periods dividing, like period doubling or reverse Hopf bifurcation. So we want to make sure our periodic points for our map are what are called uncollapsible. All right, so you're collapsible if you're Nielsen equivalent to a point of lesser period, and so you're uncollapsible if you're not. So that's one thing we need to know about periodic points. And we also need to talk about precisely what it means to persist under homotopy. So if we have a period endpoints, we say they're Nielsen equivalent if there is an arc. Now we have two different maps. And so we need to take the arc between the two. We have gamma, we have the image of gamma, but for each t, we hit it with something else. All right, so you can also formulate this in the covering space. All right, so here's the main persistence theorem of Nielsen theory. So we assume we have a Nielsen class of least period endpoints, and it's essential, means the index is non-zero, it's uncollapsible, means that it's not Nielsen equivalent to something of lesser period. And if you're homotopic to it, then you have a Nielsen class, which is Nielsen equivalent with the same index. In particular, it's non-empty. And the important thing is you preserve the period. All right, so this is the main theorem of the theory, is that essential and uncollapsible imply persistent under homotopy. All right, so this, as I said before, is the main strategy here. The first is we've understood already hyperbolicity in the cover and its implication for all the Nielsen classes to be single points. But one more implication, which is also not hard, is that if you have expansion in the cover, then all the Nielsen classes are uncollapsible, right? Because you can't, the lesser periods the lesser period points are also fixed points for the higher period, and they're all fixed by different lifts. All right, so this is the main strategy of a number of theorems, is that if you're expanding in the universal cover, or if you're a homeomorphism, you're hyperbolic in the universal cover in a way which I'll specify, then each lift can have at most one fixed point. Thus, everything in the fixed point set is alone its Nielsen class. It's uncollapsible, and then you need one more ingredient that they're essential, and so they all persist under homotopy. So this is the tool for working with many examples in higher dimensions, pseudoAnosov maps, Anosov maps, and in lower dimensions, these kind of toy examples I've been using for expositional purposes. Okay, so just go back to our examples. All our examples, the examples were there to implement the strategy. They're all essential. You have expansion in the cover. They're all uncollapsible. They're all in different Nielsen classes, so they all persist. All right, and this number of fixed points and the periodic points, etc. Remember, we can compute from symbolic dynamics. All right, so this is an example of kind of what the talks were about. If you know the action on pi1, then you get infinitely many periodic points that you can completely understand their periods, because the ones that come from the symbolic dynamics of the minimal model all persist. All right, so that's the end of the story for Nielsen theory. And Nielsen theory is all about periodic points, okay? Now, what about the rest of the dynamics? Typically, the periodic points are just a countable set, maybe dense, but there's lots of other stuff going on. So for the rest of the stuff, you need to use a generalization of Nielsen theory called global shadowing. All right, so global shadowing at this point we'll use in the universal cover and later in the abelian cover when we abelianize. All right, so it goes back to Katak. It's actually a much older idea. I follow Handel's use of it closely. The real idea for this is the Morse lemma. So if you know a little bit of differential geometry, if you're in a hyperbolic manifold and you're in the universal cover, if you have a quasi-geodesic, which means the length along the curve is comparable to the distance, then it's a bounded distance away from a real geodesic, which is to say it globally shadows a real geodesic. Okay, so that's kind of the origins in terms of geometry. Here's the actual definition. So if we have a pair of homotopic maps, we say an orbit under one globally shadows an orbit under the other. If you can lift everything to the universal cover and they stay a bounded distance from each other. So we're going to just go in forward time, but they bounce along in the cover and they stay a bounded distance away from each other with respect to some equivariant metric. Okay, so what we need is some tool that's like in the Morse lemma. The Morse lemma, the background hyperbolicity is coming from the geodesic flow, the hyperbolicity of the hyperbolic metric. So we need to formalize this thing that I've been using about the expansion in the covering space. All right, so you call something pi1 hyperbolic if there's an equivariant metric and a lambda bigger than 0. So things are growing by the rate lambda, distances are growing by the length lambda. All right, so all my examples were pi1 hyperbolic. That's why I chose them. They're all expanding in the cover. Last week, we talked about pseudoAnosov maps, which are hyperbolic in the cover. They're expanding in one direction, contracting in the other. So in fact, we first want to check that global shadowing is a generalization of Nielsen equivalence. All right, so that's something you have to prove, but you're Nielsen equivalent if and only if you globally shadow. And the global persistence theorem of global shadowing goes back to Mike Handel in the pseudoAnosov case. I already mentioned the expansion and contraction. So let's have an approach to Handel's theorem. So what we need to know is what we know thus far is we have pi1 hyperbolicity in essential classes, then all our periodic points persist. All right, so I got to extend this to all the dynamics. So the basic strategy is that there are a lot of periodic points. All right, so the periodic point behavior somehow should determine all the behavior. So the way this goes in this theorem is the hypothesis that the periodic points are dense. Okay, so here's the statement of the theorem. So let's assume we have a map of a manifold or a wedge of two circles, or in fact, a finite CW complex. First, assume it's pi1 hyperbolic. Let's have expansion in the cover. Nielsen classes are essential. And then we have our final conclusion, final hypothesis that periodic points are dense. All right, then we homotope the map. And the theorem says that for the new map, there is a compact invariant set, G invariant set Y, a continuous onto semi-conjugate C that's homotopic to the inclusion. That seems technical, that's quite valuable. So you get this diagram. All right, so as you perturb large perturbation under homotopy, your dynamics persist, but maybe not in terms of the entire set. You can have new stuff, which I'll comment on, but the stuff from phi persists in this compact invariant set. All right, so that's the theorem. So just in words, if you homotope, the dynamics don't get simpler, the entropy doesn't go down, and you don't lose periodic points, at least in low dimension. Well, you don't lose periodic points, etc. All right, so this is the theorem. Here's the idea of the proof, just to connect it to global shadowing. So this set Y, it's exactly the things that global shadow at some point in X. So you have the model map and you see for a given Y, does it globally shadow something in X? Some X for phi. All right, so you look at your new map and see if it's connected to the old map. So in the universal cover, you think you're marching along by phi and you find the map, the points of G, which stay a bounded distance away from a given phi orbit. And then you prove various facts about it. It's closed, it's invariant. You push it downstairs, it's compact. That if you define sending a point to the point you globally shadow, that this is well defined and continuous, and so the whole thing descends down. Okay, so now you have a problem is at this point, you've only used I1 hyperbolicity, right? It turns out, but now you want to get the alphas onto. All right, so now we have to use what I just told you, that the periodic points persist, and since they persist, they're Nielsen equivalent, and therefore they globally shadow. So sitting up here, you have copies of all the periodic points down here. But this guy is compact, so its image contains all the periodic points and is closed or compact, and therefore it's everything. All right, so that's the final kicker where you use the density of periodic points, where you basically say, you know, the periodic point behavior. Okay, so that's the proof. And there's just a comment on this set Y. It can be strictly smaller. All right, so good question is, how can it be strictly smaller? Well, remember your Nielsen equivalent if and only if you globally shadow. So that tells you that if you create a new Nielsen class by your perturbation, then Y shrinks. All right, it's because a new Nielsen class, which won't be essential, but it's a new Nielsen class, it can't globally shadow anything from phi, because if it did, it would be Nielsen equivalent, and we've assumed it's not. So one way to shrink Y is to create new Nielsen classes. All right, and so anyway, so Y could be strictly smaller, and in general it is. All right, so here's the remarks. All our examples were cooked up so they satisfy all these hypotheses. All these maps on the wedge of two circles satisfy the hypotheses. And so you preserve all these dynamics. And again, all you need to know is the action on pi1. So if you have the same action on pi1 for this space, you're homotopic, and therefore you have all the dynamics of the phi, which are the minimal models. Okay, so this is the main persistence theorem for periodic points and for general points. And now we want to describe the persistent dynamics. All right, so we have to use algebraic topology tools to describe the persistent dynamics. All right, so there's lots of tools for doing this. One is to go back and use Nielsen theory and the fundamental group. And so these are called twisted conjugacy classes. And these in general, it's a computation in pi1, so it's not so easy in general. And the alternative, which I'm going to mainly talk about today, is to use homology to specify the persistent dynamics. And homology depends on the tools you have available, depends on the action on H1. All right, so if you have one as an eigenvalue, for example, if you act like the identity, then you can use rotation sets so this means if you have a 1, it means there's at least a Z cover, and you can measure progress in that cover and compute rotation sets. If the spectrum of F star on homology is hyperbolic, you can use abelian Nielsen theory and Frank's theorem, which I'll tell you about today. And if just one eigenvalue or some eigenvalues are off the unit circle, then I'll talk tomorrow about how you use partial versions of Frank's theorem. All right, so you can do these various tools, and since you have a Markov partition, you can use the Markov partition in the covering space to do these computations. All right, so I did these last time, so I think I'm going to skip them now. So you can compute twisted coordinates using the action on the cover. Again, I'm going to skip this just because of the time. You can compute rotation sets. I did this last time using the Markov partition. And you get rotation sets. And the important thing is that when you compute the rotation set, the important thing for the theme of the lectures is that if you homotope the map, you can't lose the rotation set if your pi1 hyperbolic mu satisfied. So it really does describe in these particular cases the homotopy invariant and homotopy invariant dynamics in terms of action in first homology. Okay, so those are all computations and they're all in the notes. And again, as I said, the main tool here is we have a Markov partition. We lift the Markov partition to the appropriate covering space, see where the boxes go in the covering space, and then that tells us we have a transition diagram, but now it's labeled by where the boxes go in the cover, and then we just feed it into kind of a symbolic dynamics machine and spit out the coordinates that we care about. Okay, so the new thing here, so that was all kind of review of last week, is to use homology instead of the fundamental group. All right, so as we all are aware that homology is much easier to work with. It's a vector space if you're over the reals, but you lose information. Like a lot of spaces have the same homology and have very different fundamental groups, right? This is, well, higher homology. The fundamental group, of course, determines first homology. All right, so in many cases, like tori, the fundamental group is abelian. So the non-abelian and the abelian case are the same, but there's new kind of ideas in the abelian case. All right, so we want to take what we had about Nielsen theory and abelian opposite. Okay, so what does this mean? Well, we use the universal cover. That's the one associated with pi1. The set of deck transformations is pi1. Now we want to use a covering space where the deck transformations is H1. All right, so how do you do this? So this object is called the universal abelian cover. And one way to obtain it is to take the universal cover and mod out by the action. The fundamental group acts, so you can act by the commutator subgroup and mod it out. Or I'll show you a way to think about it. The wedge of two circles is particularly simple universal abelian cover. It's just the grid. All right, we'll work with that later. So anyway, so here's the example. So if you have the wedge of two circles, the universal abelian cover is just this guy. Of course, for the torus, the universal abelian cover is the plane, which is the same as the universal cover because pi1's abelian. You have a genus G surface. The universal abelian cover is kind of hard to draw pictures of, but homology, the rank of first homology is twice the genus. So the collection of deck transformations is Z to the 2G. And the feature to think about with the universal abelian cover is that if you have a loop downstairs, you'd like to know when it lifts to a loop upstairs. All right, so in the universal cover, loops downstairs never, non-trivial loops downstairs never lift the loops upstairs. But in the universal abelian cover, you lift to a closed loop if and only if you're zero in homology. So here's the usual example. If you look at the genus 2 surface, the circle around the neck here is zero in homology. All right, so it's an easy thing to check. So it lifts to a closed curve in the universal abelian cover. And for our wedge of two circles, this is the usual thing we do in complex variable. It lifts in this cover to a closed loop. All right, so now we want to take what we learned about non-abelian Nielsen theory and abelianize it and then use that for computations. All right, so the first thing is that, so sorry, this is not visible. This is supposed to go away, but it's not for some reason. So if things are Nielsen equivalent, so first there's a definition with arcs. They're Nielsen equivalent if there's an arc between them such that the image of the arc is zero in homology. So if you think about the homotopy thing, that's the same as in Nielsen equivalent, it's saying that the loop and its image is contractible. But here it's saying that it's homologous to zero. All right, so that's one definition. Now you have to be careful. If you have fixed points here, this arc and this arc, their union is 0 in homology. So these things are abelian Nielsen. Whoa. Whoa. Okay, gotta watch that. All right, so we can also use the universal abelian cover, same way we used it for Nielsen equivalents. So things are abelian Nielsen equivalent if and only if they're lifts to the universal abelian cover where you fix the 2 points. All right, so kind of obvious definition, you know the usual Nielsen theory definitions. And these are generalized to periodic orbits and homotopic maps in kind of the obvious way. All right, so this takes the Nielsen theory and just abelianize it in a fairly straightforward fashion. All right, so it's useful to have a more concrete way to think about the universal abelian cover. All right, so this is an old classical idea, basically Jacobi for Riemann surfaces. And you embed it in a natural way in R to the beta, where beta is the rank of H1. All right, so let's make it torsion free, just for simplicity. So here's how you do this. Is you assume it's smooth, so you used in Durham cohomology. You pick a basis of closed one forms. They're nice, they're dual to a basis of H1. You lift them to the universal abelian cover. So it exists, you lift them. So you take the forms, you lift them, and then you use the forms to define a map from the universal abelian cover into R for each I. And how you define that is you just pick a path from your base point. So you pick the base point. You pick a path from your base point to your given point. You integrate the form along that path. All right. And so it's a smooth arc from X0 to X1. Now you have to worry, is this well defined? What if you chose a different arc? But the universal abelian cover is exactly the one where closed forms make that, where lifts of closed forms makes this thing well defined. All right, so for each I, you get such a map from the universal abelian cover. You have beta, where that's the first Betty number of these guys. All right, and so you put all these maps together. There's a picture here, sorry. You pick a path from here to here, and you have the image of this point by integrating the particular lift of the one figure, the tilde here, and you get this point. All right, so this takes the unit, and it turns out this is an embedding. All right, so this, you put all these guys together and it embeds the universal abelian cover in a nice Euclidean space. And this has a lot of nice properties for working for computations, that deck transformations just work by the usual deck transformations that are in. So you've got this universal abelian cover sitting in this big Euclidean space. But now you think of your deck transformations on the universal abelian cover, well, they're just translation in the space. So that's what's cooked up by having the forms dual to basis of H1. All right, so this allows me to write the action on this cover as just plus n. All right, so now we no longer have to think about the deck group. We just think about the usual deck group in R to the beta. Another nice thing, which will turn out to be very important, is how lifts act. All right, so again, this isn't hard to show, but if you lift a map from M to N, right, everything lifts because they all preserve the commutator subgroup. So they all lift, but the nice feature of this embedding is that the action of the lift looks like homology times X tilde. All right, HA is the matrix, so remember we're in R beta, so we can have a matrix here. The matrix of the action on H1 plus a bounded piece. All right, so this piece is equivariant in this sense. As you move by a deck transformation, you get the same answer. So what's very important for the theory is this guy is bounded. All right, this is a bounded function. All right, so well, what this is saying is if you have a map, then it's basically looks like the action on homology plus a bounded piece. All right, so this is going to be really important when we have hyperbolicity, because this bounded piece is going to get washed out by the hyperbolicity, and we're just going to get this guy remaining. All right, so this is how you deal with the universal abelian cover of a manifold. Just a nice clean way of writing these formulas, which when I get to Frank's theorem will be very valuable. For the wedge of two circles, this guy kind of sits in R2 in the obvious way. And it's not a manifold. It doesn't have, have to fuss to get to Rom cohomology, but it lives naturally in R2. All right, and the deck and the lifts and everything works the same way. Okay, so another important thing is what happens, and again, usually you do this in general from algebraic topology, but because you have this form for the action of the lift, that if you want to see what the lift of a translatable point, which is the same as the deck transformation acting on it, then when it comes outside as A times N, all right, where A is the action on first homology. Okay, so this is the definition of abelian Nielsen classes, and we have a tool for working with them in this nice embedded version of the universal abelian cover. All right, so what's the coordinate we're going to use? All right, so first we need an equivalence relation on Z beta, and this equivalence classes will be our coordinates for abelian Nielsen classes. All right, so what they are is the twisted class, as it's called, of a vector n is we look at all possible other vectors and we do am minus m plus n. All right, so I didn't talk about twisted conjugacy for pi1, but this is the abelianization. So the thing you notice immediately is that two classes are the same if and only if this formula holds, which is to say their difference is in the image of A minus I. All right, so this equivalence relation turns out to be exactly the coset in this quotient group. All right, so this group, this formula will come up over and over again. But it could, it could be finite group, infinite group, whatever. But the set of coordinates, Nielsen coordinates, are exactly this guy, where A is the action on first homology. All right, so how do we give coordinates to abelian Nielsen classes? Well, just like linear algebra, you have to fix a lift. So we fix a lift, and you see, we pick a particular lift of X and see where it goes in the cover. All right. And then it's abelian twisted class. Its coordinate is the coset in this group corresponding to the translation. All right, so now you have to check, which is not hard, that if you choose a different lift of X, then you get a different N, but this N will be in the same coset of this group. All right, so I proved this here, but I think it's fairly straightforward. I'll prove something later, but you just kind of write down the formulas and it follows immediately, using the fact that when you shift by a deck transformation, you hit it by A times the deck transformation. All right, so it's expected. So the whole thing is supposed to work so that if you're abelian Nielsen equivalent, then you have the same coordinate. All right, so they have the same coordinate, and that's equivalent to being abelian Nielsen equivalent. All right, so this is just what we want. We have a good set of coordinates which distinguish and specify abelian Nielsen classes. Okay, so think about, I'm going to prove something later. I think I won't prove this one. Once again, this you just run through the definitions, and it's just a definition chase. It isn't hard at all. Okay, so yes, we make a break. Yeah. Thank you. where we are is we've taken a dynamical system, used its universal abelian cover to associate to fixed points or periodic points, in fact, elements which are coordinates of their classes in this group. Now, so that means that if we look at a given F, we can look at what its collection of all possible abelian Nielsen classes, and they're all cosets in this group. All right, so this is the space where the coordinates live, but there's no claim that all those classes are non-empty. All right, so for a given F, some of these could be non-empty. All right, but choral automorphism and endomorphisms are a special case where in fact, none of these are empty. And in fact, we'll be using Frank's theorem to compare a general map to a toral map. All right, so here's our example. Let's look at a matrix over the integer and assume one is not an eigenvalue. All right, you'll see the reason for that in a minute. And this guy is invertible, is the same as one not being an eigenvalue. In the standard way, we look at the induced map on the N torus. And so the action on H1 is exactly this matrix A. So this is the usual setup. And what does our collection of abelian twisted classes look like? It looks like this. Now, the whole point of not having one as an eigenvalue is that this guy is invertible. And then if you've taken algebraic topology, simplicial topology, you know how to compute this guy using the Smith normal form. Right? So if one's not an eigenvalue, this is a nice finite group. All right. And it's a nice finite group. And for the torus, let's check what elements are represented by twisted classes. All right. So we're looking for a fixed point. In other words, a point which lands on a deck transformation of itself. Notice we're in a Euclidean space, so we write it like this. We can simply solve this equation. This guy is invertible. That's where we're using it again. So every twisted class, which was to say every N, has a fixed point in it. And they all have non-zero index because the index, remember, this is a formula we did before on the index of a smooth map. So every abelian Nielsen class in the torus is full and essential, and they all have this same index. And in fact, the Lefschetz formula, you have to do a little algebra to see that the Lefschetz formula is this. So in higher dimensions, it's a little trickier, but you see the Lefschetz formula sees all the fixed points. And whoops, gotta watch that. And all the abelian Nielsen classes are full. Okay, and each one has exactly 1 point. So this is the glory of the tori, where everything's as nice as you can imagine. All right, now this group comes up in a different context, but in fact, it's not a different context. It's the same context. If you go back to your algebraic topology and you compute the homology of the suspension manifold, what you find is that you get exactly the same group here, plus the factor Z, which is the circle direction of the bundle. I mean, the base of the, anyway, so you get that circle there. So this first factor is exactly the collection of abelian Nielsen classes. Okay, so it's not surprising, and again, you can just prove this, that the abelian Nielsen classes are telling you whether the periodic orbits are homologous as closed loops in the mapping torus. All right, so if we go back to our toral cases, where one's not an eigenvalue, then this is initially a strange fact, but the suspension manifold is mostly torsion, right? There's a finite group piece here. And so that means there's a finite number of homology classes for each period, this is keeping track of the period. So each homology class contains a periodic orbit. All right, so that's again the glory of tori. When you suspend it, every homology class for all periods contains exactly one periodic point. Periodic orbit. Remember, periodic orbit now is a closed curve in the suspension. All right, so tori are very special, and everything is nice and understandable, and everything's full. And the Frank's theorem, which you've heard referred to, takes your given dynamics and compares it to this toral dynamics. Okay, so let's just do an example here for concreteness. So remember, we have this map on the wedge of two circles. Here's its image. We do the trick that I said before. We lift to the universal abelian cover now, which is, remember, just this grid. We see what's happening to fundamental domains or Markov boxes if we subdivide. So we take its image and we see that there are 5 fixed points, and that also comes out of the Lefschetz formula. 6, the trace is 6 minus 1, so the trace is 5. So there's a fixed point here, then this gets stretched over. So there's a point here which goes to its deck transformation there. There's a point here that goes to its deck transformation there. Same in this direction. So if you write these points, you just use the coordinates here, you see that in fact these are your 5 fixed points. All right, so your 5 fixed points in the usual coordinates are right here. Remember, this is multiplication by 4 in that direction. All right, so there are your 5 fixed points. And let's compute their abelian Nielsen classes. I made this comment already. You see those 5 points from the Lefschetz formula. And what's the group here that's containing your abelian twisted classes? Well, again, you have to compute the Smith normal form, or you ask your favorite computer to do that for you. And you find that the collection of abelian twisted classes is actually Z3. Okay, so there's in fact just 3 of them, but we have 5 fixed points. So it must be the case that 2 of them, that some of them are in the same abelian Nielsen classes. So how do you compute abelian Nielsen classes? You pick a point, for example, 1/3 0. Its image under phi tilde is 4/3 0. You just compute that from the picture. That's your original point plus this deck transformation. All right, you do that for every, so that tells you, let me back up, that tells you that its twisted class is the group here, the quotient, the image of F star minus the identity, and plus this deck transformation. You do that with each of them, and you get a priori 5 different twisted coordinates. Okay, you have 5 different twisted coordinates, but in fact, you only got 3 slots to put them in. All right, so some of them must be the same. So in fact, you can just compute that the difference between these 2 deck transformations is this guy, which remember is A minus the identity times this guy. All right, so they have this, they're in the same coset. So they have the same twisted class, and similarly for this. All right, so there are 5 fixed points, but pairs of them are in the same Nielsen, abelian Nielsen class. So they're all in different Nielsen classes, but when you abelianize, some of them match up. All right. Now, so there you get overlap. Now for periodic points, there's a different story, because the number of fixed points, remember, is the Lefschetz number here. And it turns out they're equal because of the action on H1 is this number. Now, we got to compute this number. This is the number of fixed points. You can get this from the symbolic dynamics. You want to compute this number. Well, you compute the eigenvalues. They turn out to be 2 and 4. So this absolute value is this. All right, so now let's see how many twisted classes there are. This is the number of fixed points. Number of twisted classes, we have to compute the order of this group, which, if you know about Smith normal form, is the size of the determinant of the subgroup here. What's a lattice in this case? The sublattice. And once again, you use what you know about the trace. And you see that the number of classes at phi to the n is this quantity. Again, using, you just expand with it. Well, I expanded it for you. It's just 2 by 2, so you get this formula. All right, so this is the number of fixed points. This is the number of classes. So it's fairly obvious that the number of classes is growing much faster than the number of fixed points. So for higher iterates, for example, just n equals 2, there are 19 fixed points, and there's 45 slots for them. All right, so the toral, what I should say is the toral automorphism with this matrix has all 45 slots filled for the second iterate, but our particular map only has 19 of them, and they still could overlap. I just don't know. I didn't do the computation. All right, so I keep plugging this idea is to take our given map and compare it to a toral automorphism. And that goes back to what was actually John Frank's thesis. He used it in a kind of different way, but the argument is completely his. All right, so here's Frank's argument in this simplest case. And we're not going to use a fixed point argument. I'm going to use a series just because it's a little more manifest. So remember, this is the action of our map in the universal abelian cover, thinking of it as living in the plane, all right, with this guy bounded. All right, so we want to understand iterates like we always do. So we iterate, we induction, we get this formula, and then you say, aha, well, this a to the n term is dominating. So let's normalize by it. So let's multiply the whole thing by a to the n, a to the minus n, right? We get this guy or a summation formula. So we just iterate this guy, hit it with a to the minus n, and we get this. All right, now the important observation is that this guy is bounded. That's why I emphasized it before. And this guy, it's both its eigenvalues are outside the unit circle. So when we take the inverse, the spectral radius is inside the unit circle. And so that means that this series converges to a continuous function. All right, so it converges to a continuous function I'll call alpha tilde. All right, so this is somehow the infinite iterate, right? We're taking the limit of a to the minus n times phi to the n. So we have a normalized infinite iterate. And the amazing thing is it converges to a nice continuous function. All right, so lots of properties follow immediately from the construction. It's continuous, as I said, from Weierstrass, maybe it's from Weierstrass M-test, essentially. It acts like this with respect to deck transformations. That means it's homotopic to the identity. And a simple computation says that if you do a alpha tilde, we do a times this limit, we bring it inside, shift indices, and we see we have alpha tilde phi tilde. So just by kind of following our nose, computing this normalized infinite iterate, we get a commutative diagram like this. And everything descends because of the way it works in the covering space, everything descends. And so we get the original map on the wedge of two circles, a map alpha, which is continuous, we don't know much more, and its image is down here. All right, and its image is invariant under the toral automorphism induced by phi a, right? So that's what, because this is what's happening on the plane. When we push everything down, we see that it's the toral automorphism in phi sub a. All right, so we've semi-conjugated our map to something which lives inside the torus. All right, so that was Frank's story. Using it, and I'll tell you more about it in the next lectures and how to jazz it up and put various applications. So the question is, I mean, what's the image look like? All right, and what is it connected to the abelian twisted classes? So it turns out it's very basically, it's giving coordinates for the twisted abelian classes. And so Frank's map and abelian coordinates, abelian Nielsen equivalents, are basically one and the same story, at least for some classic maps. All right, so what does the image look like? So you can do this on a computer, and this is what it looks like, and this is the universal cover, so you get all these guys. So you think of this guy. So this guy is invariant under the action of A, or when we have another picture, this is what it looks like in the fundamental domain. And this guy is invariant under now the endomorphism of the torus induced by 3, 1, 1, 3. All right, and you'll notice there are some intersections here. And in fact, as you do more iterates, these guys intersect. So it turns out that these are exactly the pairs of points we discovered with the same abelian class. So the theorem to come is that the value of the Frank semiconjugacy is the same if and only if for periodic points you're abelian Nielsen equivalent, or you have the same abelian Nielsen class. All right, so this is what the pictures look like. You can see it's very non-smooth. This is just the fifth iterate. So as you go more and more, it becomes nowhere differentiable, nowhere locally BV, and all sorts of things. All right, but this is the image, which is capturing somehow the dynamics in a way that I'm going to explain now. Okay, so what are the observations we want to make, and how do we connect it to abelian twisted classes? All right, so the first thing is that if you have periodic points for the original map, their image is periodic in the torus. And now the observation I've kind of been pointing to is that the collection of all possible twisted classes for phi1 to the n is the same as the classes for the torus. All right, there should be an n here. All right, so we've taken our given map. It has some twisted classes, and it turns out only some of these guys are full, and it's the ones that are full are sent over here by alpha to the classes over here. All right, so for our given map, a lot of these are going to be empty, and of course the torus is not empty, but our map alpha is going to take these classes to those classes. Right, it's going to induce a map on the twisted classes, well defined. Okay, so here's the first observation, fairly simple, that if we have our point X, we hit it and it moves by n. So this gives the class. All right, so we compute phi of this guy. So phi tilde of this, we want to compute the class of alpha tilde of x tilde. This guy comes out because this is the semiconjugacy. All right, well, this guy is exactly x tilde plus n. This is homotopy, the identity, it comes out. So this tells us exactly that phi acting on this point, phi tilde acting on this point, moves it by n, which is to say, as I've been saying all along, that the twisted class under phi1 goes to the same twisted class. Remember, these are in the same group. That's the previous observation. Goes to the same class over here. And of course, it extends to periodic points. Okay, so that's all good. So we preserve, this is another way of saying this, is we have an induced, alpha induces a map from twisted coordinates to twisted coordinates. It's well defined, but it's clearly not onto, it's into, right? So instead of those complicated pictures, we can look at this algebraic fact for all n, how these guys are mapped inside here. All right, so periodic points are fine. And it's even stronger than this, that your Nielsen equivalent, if and only if your image is the same. So I alluded to this before, but 2 points, 2 periodic points, have the same abelian Nielsen class, if and only if their image is the same, right? So in the original I showed you for our map, there were pairs of points which had the same, were in the same abelian Nielsen class because they have the same coordinate, their image coincide over in the image. Okay, so let's see a little bit of the proof here. So let's say we're a billion Nielsen equivalent and see what we can get with that. Well, we saw already if you're a billion Nielsen equivalent, then of course your twisted coordinates are the same. And then I've observed that when you take the image, your coordinates in the torus are the same. But now you use the fact that we've mapped into a toral endomorphism that's expanding, right? So phi to the n can fix at most one point, right? So it must be this point, and so these 2 points must be the same. All right, so we're using the hyperbolicity in the image, which is coming from the hyperbolicity of the action on H1 of our original map. All right, now the other way is actually obvious, so let me not do the other way. All right, now, as with the Nielsen theory, we want to talk about not just periodic points, but every point. These ideas go back to Gavin Band, which actually he was a postdoc here. He thanks Felix in this paper. He was at IPAN for a while ago. So this is what it means to abelian globally shadow. We just do the obvious thing. We do global shadowing, but in the universal abelian cover. So 2 points are abelian globally shadow. If and only if we can lift them to the universal abelian cover and they stay a bounded distance apart. All right, just like using the universal cover, you can do this in any cover, but we're using the abelian cover because this is the one connected to homology. All right, and so here's the fundamental fact then. You're a abelian Nielsen equivalent if and only if the image of the Franks map is the same. All right, so this tells you what the Franks map is. It's the same as the Handel map I told you about. I told you about earlier in the lecture. It takes a point to the point of phi. Well, actually, this is we're still with the single map phi. So let me withdraw that comment. All right, so your abelian Nielsen equivalent if and only if your map is the same. So I'm going to make that comment later. Okay, so let's see how to prove this guy. Once again, we thinking of our abelian cover sitting in our beta, and we are going to, instead of doing an equivariant metric, sometimes I'm just going to use the norm in R to the beta. All right, so let's see at least one way with this guy. So let's say your image is the same, so there's supposed to be a prime here. Now we have to remember that the map alpha tilde is x tilde plus a bounded piece. All right, so that was the formula when we took that summation using the Weierstrass M test. This semiconjugacy looks like the identity plus a bounded piece. All right, so if this guy equals this guy, then these are the same. All right, and then we use the fact that this is bounded, right? Since these are equal, we bring this over, use the max of this, we get that the distance between x prime and x, so assuming this, you get the difference between x prime and x is less than or equal to twice the max of this, which is c. All right, but on the other hand, if this is equal to this, we hit it with A, and then use the semiconjugacy, we get that this equals this. All right, but now we use this little fact above. Alpha of this and alpha of this are equal. And so alpha hitting, because alpha is a bounded distance from the identity, this stuff inside is less than or equal to C. It's the same argument there. Then we just run an induction and you see that you're always less than C for all iter. So assuming that the Franks map is the same, using the structure of the Franks map, you get that it globally shadows. Okay, so now let me let me skip the other way. The other way uses the expansion in the image in a nice way. Okay, so that's not done. All right, so let's summarize now where we are. So for periodic orbits, watch that. For periodic orbits, remember we're Nielsen equivalent if and only if our image is the same. And for all orbits, we globally shadow if and only if we have the same alpha image. Okay, so this is all about our original map phi telling us what Frank's map is in terms of this new notion of abelian Nielsen equivalence. Okay, so now assume, let's go back to our main theme. So now we only know that G is homotopic to phi1. It acts on pi1 with the same action. All right, so let's go back and learn what we know from Nielsen theory. So we know from Nielsen theory, we had the persistence of all its periodic orbits. And so since they're persisting under normal Nielsen theory, they persist under abelian Nielsen theory. Okay, so what we want to do is perturb our map. All right, so we perturb our map, and I want to compare the alpha of our new map with the alpha of our model map phi. All right, so we do the same game with G. Now, since G is homotopic, it acts the same on first homology. So its formula on first homology is the same, but with a different bounded piece. All right, so not thinking in the background, if you have homotopic maps, it means in the cover, there are lifts, they have equivariant lifts that are a bounded distance away from each other. So we can run Frank's on this guy just as well, because all it depended on was the action on homology, which was A. All right, so we run Frank's argument on this G, and we get a commutative diagram that looks like this. All right, but remember we have this persistence theorem, which tells us that periodic orbits persist, global shadowing persists back in the pi1 theory. It all comes to the abelian theory. So the upshot of all this is that if you homotop the map, then, sorry, one of these is wrong. This should be alpha phi down here. That's alpha phi. That the Frank's map, the image of the Frank's map just gets bigger. All right, so it's like rotation sets, if you remember from last week. That this map, the image of this map alpha is capturing the dynamics of the asymptotic abelian dynamics. And as you perturb it, it only gets a little, this should be an X. Boy, this is messed up completely, sorry. This should be a phi1, this should be an X. Let me just write it correctly on the board. So alpha G X is contained in alpha E of X. All right, so this is an expression of the persistence theorem, right? Of the persistence. So the whole goal here was to find coordinates. So this gives a set of coordinates, asymptotic coordinates, the image of the Frank's map, which encapsulates all the dynamics of the map. And then we homotope it. And since it's the simplest map in its class, all its abelian Nielsen classes all persist. So the image of any map in its homotopy class is at least as big. All right, so this again emphasizes why this object here is really a coordinate for the homotopy invariant dynamics, but now in homology, not pi1. Okay, so I did all this for the particular map phi1. All right, now there's not a whole lot special about phi1 except its action on homology was expanding. And of course, Frank's original version of his theorem is much more general. So the next thing to do is to go back and really look at Frank's theorem in the most generality, and then kind of jack it up and anyway, should put more consequence. Okay, so this is now in the last 10 minutes or so, tell you about Frank's theorem in general. All right, so first we need the action on H1 needs to be H1 hyperbolic. All right, so what it means to be H1 hyperbolic, remember, we always need some kind of hyperbolicity, at least in the algebraic topology, to get these arguments to run. And so we look at the action on H1 and could be that all our eigenvalues are outside the unit circle. So that's what most of our examples were. They were homologically expanding. Now, you can also deal with the case that your eigenvalues are off the unit circle and your homeomorphism. All right, so the stuff inside the unit circle is expanding for the inverse. So you can be in either of these two cases. Now, the thing you have to worry about here and not say is that if you have an endomorphism with spectrum inside the unit circle, you don't have any way to deal with it. And in fact, the basic theorems aren't true anymore. If you've got stuff inside the unit circle and you're not a homeomorphism. Okay, so this is our setup. Eigenvalues outside the unit circle or everything off the unit circle for homeomorphism. All right, some standard examples, maps of degree n, so homology is outside the unit circle. You construct a linear topomorphism, either an invertible matrix, in which case you're in this case, or a matrix with everything outside the unit circle, you're in that case. Phi1, so remember our action for our first example on homology was this. All its eigenvalues were 2 and 4, all outside the unit circle. You can construct homeomorphisms of the torus where your action looks like this. We'll see examples of that next time, explicit example. So here's the theorem. So here's Frank's theorem in, well, pretty much the most general form. So we have a continuous map of a finite CW complex, and we're assuming it's H1 hyperbolic. So we've assumed what its action on H1 is. Then there exists this map alpha from X to the torus of rank of dimension beta, where beta is the rank of H1, and such that this guy commutes. And this toral map is induced by this matrix A, which is the action on H1. All right, so very general theorem about, but you need, at this point, you need fairly strong conditions on the H1 spectrum of F. But given those, then you get this semi-conjugacy, but the mystery is what this image looks like. All right, so we saw in special case what the image looks like. So in general, it's some strange fractal object. Okay, so how does the proof of this go? I'll speak about this next time in more detail, but basically we've already seen how the proof goes. You act, if you're strictly expanding, you compute this limit. And that gives this guy, you write the sum out and you get a convergent series. Or, again, you have to do all this in the covering space, universal abelian cover. Or if it's a homeomorphism, you have to split into the expanding and contracting subspaces and doing the unstable stuff and the stable stuff. And you have to be careful with expansion and contraction, but this is where you very much need a homeomorphism so you can write the inverse. All right, so in fact, Danu said you could do this with a fixed point argument, which is fairly obvious here. But you find the fixed point here because this guy is expanding. Anyway, so as I said, next time we'll talk more about the proof, but in fact, it's not hard at all for such a kind of surprising theorem. The proof is quite easy. You're right. If you want more properties of alpha, you have to work harder. If you want to get it older or other things, you need a little more work. All right, so the corollary is the one people often refer to as Frank's theorem. If you have a toroidal map and it's H1 hyperbolic, so either it's invertible, this is now its isotopy class, its action on H1 is invertible, and it's a homeomorphism, or it's outside the unit circle. Then there's this map alpha Tn to Tn. So now alpha is onto basically for dimensional regions, where now this induced map on the torus is the toral automorphism corresponding to the action on H1. All right, which is either hyperbolic or expanding by hypotheses. Okay, so this is the version that's used the most. It tells you if you're homotopic to a toral automorphism, hyperbolic toral automorphism, then you're semi-conjugate. All right, very useful theorem. All right, so let's make some remarks about this and how it's connected to what we talked about before. Now this toral automorphism is also pi1 hyperbolic, going back to the beginning of this lecture last week. So we could apply Handel's theorem to get this subset Y. Then the question is Y all of Tn, right? We're used to this picture, but why is this all of Tn and not just some subset Y? Well, I made that comment that to make Y smaller than everything, one way to do that is to create a new Nielsen class. All right, but we've seen that on the torus, all Nielsen classes are full. Right, and so by Nielsen theory, all the Nielsen classes of this guy are full already. You can't create any new Nielsen classes because they're already all full of orbits because we're in the torus case. All right, so this is just that comment that all the Nielsen classes are full because this group and this group both have points in all their cosets with coordinates in all their cosets. All right, so you can't create any new Nielsen classes, so your set Y is actually everything. Now, another way to think about this is due to Jarek Kłapisz, just a comment he made to me some years ago. You can think about this in a standard hyperbolic theory, right? If your F is homotopic to this toral automorphism, all right, so let's lift everything to the cover. That means you're equivariantly homotopic to this linear map. All right, so what that tells you, now we're in the plane. We're not in some weird universal Billian cover, we're in the plane, and we're in the torus. So that tells me because they're equivariantly homotopic, they're uniformly bound, their distance is uniformly bounded. All right, now what does that mean? It means that if you take any orbit of your homotopic map GF, then it's a bounded distance away, in particular, this particular bounded distance from the toral automorphism. This distance now is C because they're equivariantly homotopic. All right. So what does that mean? It means that every lift of F, every orbit of F tilde is in fact a pseudo orbit for A. All right. Now you're in this nice homogeneous cover. Everything is hyperbolic. So there are no bounds on your shadowing constants in standard hyperbolic theory. So every orbit of F, which is a pseudo orbit of phi tilde, is globally shadowed. All right. And so, or it's shadowed in the cover, which is the same as globally shadowed. All right. So you can think about it in this way too, why the theorem is true. And then you have to turn global shadowing into a map. All right. So, okay. All right. So that's Frank's theorem. And let's see. I shouldn't go much longer. Let me see what I have to say here. All right, so I think actually, so that's Frank's theorem, and then we're going to see how it's connected in general to abelian Nielsen classes. And probably, let me stop here. And then next time I'll come back to implications of Frank's theorem, abelian Nielsen theory, apply Frank's theorem to individual eigenvalues, talk about a theorem for pseudoAnosov maps where Frank's theorem gives transverse Holder distributions to a pseudoAnosov map foliations. And then if there's time, do some fluid mechanics again to take it back home. So I'll just stop there. Thank you.